Good afternoon, everyone. It's a pleasure to announce today's power seminar. We have our dear colleague, Ernie Lewis from Brookhaven National Lab here giving our talk today. And I have known Ernie, I don't know, 15 plus years. And what, connects us is our fundamental view on aerosol physics and chemistry. And I was always wondering about that, and I didn't know your upbringing in terms of education. It's quite similar in a way, maybe therefore we tick in the same way, because Ernie did his physics in Caltech, and then he went to Europe and he got a diploma. I explained that diploma at the very famous Von Karman Institute for Fluid Dynamics in Brussels, Belgium. And diploma at that time, the older generation, the Europeans switched to the Anglo-Saxon system. It's like a master's, but with all the classes from the PhD, and it's a longer master's thesis. And we both went through that, and actually it's more valuable classically, like a master is much more effort. But now I'm saying that we have master's degrees. And then you went to Texas, the University of Texas, to do more theoretical physics graduate studies. Ernie did a lot of things. I didn't really know. That was before my time. He started off in ocean sciences. And as a matter of fact, he put together with Wallace this program, CO2 Assist, a standard program in oceanography community to calculate ocean carbon system parameters. Has been cited thousands of times. That seems to be the standard. From what I know him is, of course, the famous sea salt book with Steve Schwartz, trying to get everything about sea spray aerosol together on a fundamental basis, accounting for wind velocities, fluxes, etc. And that is also as a standard textbook. Well, and then of course, lastly, Ernie organized the Access meeting in the atmospheric chemistry community, and here to be right, this the last 10 or 12 years. That is the Atmospheric Chemistry Colloquium for Emerging Senior Scientists. And they select every 2 years the 20 best, international 25 best atmospheric chemists worldwide, a pretty harsh competition. But if you look back the last 30 years, most of these people select are successful scientists and still around. Yeah, and there's some other one in the faculty too. Well,
Daniel was actually before my time.
Yeah, 2003 access member. But anyway, that was not about me. But that is a huge responsibility. It really boosted the community for a long time, selecting these people who are true scientists and want to go on with science. And we lost your battery here. Let's plug that in again. Let's see. You see, it's speechless, even the microphone.
Ernie will stop work.
Yes. Let me do it. Two experimentalists.
Yeah.
You see.
Took the irritation trying to put a battery.
Oh, they stuck something in here. It's modified. Okay, good.
There we go.
There we go. In principle, these were my last words. So we are ready for his seminar today. So it's a real pleasure having you here. And Ernie will talk about some fundamentals about Mie scattering, and it's all about Mie in a new way of looking at Mie scattering. Thank you, Ernie.
Thank you for the very kind introduction. I appreciate that. Thank you all for being here, your attention and your time. I'm going to talk about one of my favorite topics, which is Mie. And I've been talking about or trying to learn about Mie for many years, and I will give an unconventional seminar today. Let's say that it's going to be partly tutorial. A lot of grad students here I see are undergraduates. How many people know something about Mie scattering? Audience participation. Oh, lots of people. Uh-oh. Okay. Well, you can correct me when I'm wrong. So let's see how we're doing here. No.
Just a page down or arrow down.
Yeah, the arrow down's not just the first one. You gotta work it. Wake it up.
Let me see.
Or wake it up or something.
Maybe the mouse is not on it. And now, yeah.
There we go. Okay. So these are my goals, to give a little bit of basics of Mie scattering. So in a way, it's kind of a tutorial to give some physical insight, because Daniel and I were talking this morning, and we want to understand things from a basic level, not just, here are our equations, let's plug them in. And then a new approximation I have and what I can do with it. So it's like, have I done anything to talk about? It's like, I think I have. And there won't be much time for that, but there'll be a little bit at the bottom. Okay, oops. A lot of math, which I don't expect you to understand. I'm just going to show it just to show you how the sausage is made. But there's going to be some physics, and I hope you understand that. I was out walking last week, one morning, and I saw this, and I was trying to think about what am I going to talk about, how I'm going to do it. I look at this, I go, this is perfect. This is light scattering. It looks like you can see the air. Now, we don't see air generally, so we see particles in the air that are scattering light. And I'm looking at this going, okay, it's brighter here. You can still kind of see it over here. Then I'm thinking, is it brighter because the scattering is more in the forward direction with the sun, or because I have a longer path length? So all these questions come up. Light scattering, of which Mie scattering is a specific type, is very important. It occurs all over the place. We see it all sorts of places in the atmosphere. We're all atmospheric scientists. Clouds, why are they white? Why is the sky blue? Why is the sunset red? Why do we have rainbows? It's a cloud killer I saw once in Minnesota. It was really cold and it just looked like a spotlight going up in the air. What causes that? And then we get some really neat colors here. Some smoke, which is partly absorbing, but we're getting scattering of light off of those particles. So scattering of light is very important in all aspects of what we do, certainly in climate. In their laboratory, a lot of the aerosol instruments, we use scattered light to tell us either the size or just to count them. So it's ubiquitous, we can say that. Okay, this is what we have, light scattering from a particle. This is my particle, and I've drawn two shapes and two colors. It's not necessarily a nice particle. We don't know what it's made of. It's just a generic particle. I have incoming light of a certain wavelength. It could be perpendicular or parallel polarized. I scatter off this, and then this shows the contours of where my energy goes. And if I have a light coming from this way, for instance, and here's my spherical particle, theta is the angle up this way, and phi is the angle around this way. So in general, this is our problem. We have a lot of different things going on that we want to describe mathematically. So what do we want? I want the total scattering cross-section. I'm only going to talk about scattering in today's talk. I want to know the phase function, which tells the angular dependence of the scattering. So how much is my scattering cross-section? It has dimensions area. So what does that mean? What is my cross-section? Well, I have a wave coming like this. Let's say it's coming through the room. And for every, let's say, square meter, I've got 1 joule per second going through. And I scatter some of that energy. And I look at what that equivalent area is. Now, simplistic, we'll get to that. So it's this energy scattered by a particle divided by the energy density. It tells us what effective area gets scattered. We also have where that scattering goes, and that's our phase function. That gives our angular dependence. And these depend on all sorts of things. It depends on the shape and the orientation and the composition of the particle. Depends on the chemical and physical mixing state where the substances are arranged in there. And it depends on the wavelength and polarization of light. Okay, it's easy to make things hard. The goal is to try to make them as simple as possible. Okay? That's what we want. This is a hard problem. We're going to try to simplify it. How do we make things simpler? Okay. The whole spherical Tau approach. If you grad students don't know this, talk to anybody above it. As physicists, we always do spherical Taus. So the particle, I'm going to assume my particle's spherical. I'm going to assume it's got a uniform composition, so it's got a single index refraction, m, which I'll talk about more. I'm going to assume my light is a monochromatic plane wave. I'm going to forget about polarization. Now, these are all very important things for your LiDAR, for your everything else. We want polarization. It tells us a lot of information. It's going to be hard enough as it is, right? So things will get complicated anyway. So we're not trying to make them simple. We're just trying to make them simpler, as simple as we can without losing some of the physics. So we're going to talk about this one angle theta. I have light coming in, and it's going to scatter the same in any direction, but it's going to scatter differently if I go this way. And we have one wavelength. We don't have any polarization. So I want these two quantities, the scattering cross-section, the phase function. And that tells you pretty much what you need to know. And again, a plane wave coming in this way. I'm hitting a sphere of diameter d, index refraction m, and I'm scattering light off of that. Just to set up the problem of what we have. Okay, so I really want not the scattering cross-section, but I want a dimensionless quantity, which is the scattering efficiency, which is called Q. And Q takes my scattering cross-section and divides it by the cross-section that this particle sees. So if I have energy coming in and hits my particle and it scatters enough energy that's this big, but my particle's only this big, then my efficiency is greater than 1. Okay? Efficiency is the big one. It's dimensionless. So now that's going to be the quantity I deal with from now on. Another title for the talk is It's All About Q, but that doesn't have the same ring to it. But we're going to talk about Q. Most of this talk is just about Q. How do we determine Q? Okay. Ideally, we think it's this. I have my plane wave coming in. This scatters some, so I've got this much scattered and blocked away from there, right? That's what we conceptually think of in our middle picture. Doesn't work that way. Life would be easy if it did, and I wouldn't be up here giving the talk, but it doesn't work that way. Why? Because light is a wave, and it diffracts, and it refracts, and it interferes. And remember back to your physics, all this complicated stuff of diffraction patterns and bending around corners. This is what we have to deal with. So I was talking to Daniel this morning on that. It's like, I have no intuition on this. I've been working on this for 25 years, and I struggled to try to get any physical intuition on why things behave the way they do. So I've had to go about it a different way. But here's Mie theory. Mie theory is a mathematical formulation of the scattering of an electromagnetic wave by a homogeneous dielectric spin. It was done by Mie, published a paper in 1908. Debye published a paper the very next year. Like everything else in physics, that doesn't mean they did it first. Mie has credit for it, but this was done several times. This is Gustav Mie. He went on to do some other things, but not a big name in physics. Okay, what's an electromagnetic wave? We know this. It's an oscillating electric field. My electric field is pointing up and down. I have a magnetic field perpendicular to that going back and forth, and they're moving perpendicular to both of those at the speed of light. The distance between two maxima is lambda. This is basic waves. We know this, right? It propagates, and this is going to work for any type of wave. Okay, this is Mie scattering works for visible light, which we care about, mostly for aerosol stuff. That's where most of our solar radiation is, 400 to 700 nanometers. But it works for everything, microwaves, radio waves, X-rays, gamma rays. They all talk about scattering of light from objects. So Mie scattering works for this entire range. We're going to focus mainly on this because I'm an aerosol guy. Okay, what's a dielectric? That always puzzled me, dielectric sphere. Dielectric just means it's not a conductor. What happens in a conductor? If I put an external electric field here on a conductor, all the charges go to the surface, right? It pulls them out. I got free electrons in there. They can move. They all go to the surface. The electrons, and I think I got this consistent, go from the arrow of the electric field to the other side. They go up, upwind. Okay? So internally, my electric field is zero. What's a dielectric? Okay, well, it polarizes this. My dielectric has a polarization. The electrons go part of the way. They're not free. They're not free, so they'll pull a little bit. And now I have an external electric field this way. I've got a polarization vector going from these positives to negatives because they're separated. And my field in there is not zero, but it's not quite as big as that. And this took a lot of thinking, so I'm going to spend some time on that. What is polarizability? This is my typical atom. The positives and negatives are right on top of each other. There's no dipole moment in a simple one. I put an electric field on there that's not zero. Charges separate a little bit. My polarization is a measure of how far they separate. Okay. I have not worked Kelvin, but I thought he was a pretty bright guy. I need a mechanical model. I need a little picture in my head. That's always the way I've looked at things. I got to have a little model so I know what's going on and I can do a little simple one. So with this prospect in mind, here's my model of electromagnetism. Okay, you got to work with me on this. Okay. Ions are people. Dogs are electrons. Squirrels are your electric field. And polarizability is leashes. So this is a person walking a dog. That's an atom. Okay? Little mental construct. You're at a dog park. You got three people with the dogs on a leash and one who doesn't have a leash. And this is your fence. Okay? You're out walking your dog, and what happens? A squirrel comes up over here, and all the dogs take off to that side. Right? This is a conductor, so he goes right up to the fence. He's stretched by various amounts. Okay? Everybody's with me on this? Now, you got a squirrel on the other side. They all go the other way. And this one runs up to the fence because he's a conductor. Now, squirrel goes back to that side. They all run to the fence. But he's with me. This is my simple little model. So this is a low polarizability. This is a stronger polarizability. This is a very strong polarizability. And this is a conductor. Okay? Works for me. Okay. Now let's look at atoms or particles. My dielectric particle. Okay. I have an electric field going this way. So in this one, there's a little bit of separation. The negative charges moves up a little. My positive charge kind of has a lot of mass. It's a proton, so it doesn't move much. My negative charge moves a little more on this particle, and this particle moves a little more. On this particle, it moves to the very top, the surface, okay? Now I put electric field go in the opposite direction. I'll go the same amount of distance, but different direction. Go back to my first, and I get the same thing as I do here. So now a little more physical is my dogs. I have a low polarizability, medium polarizability, high polarizability. These are conductors. They go to the surface. Okay, so this is what's going on. We have electric fields that are moving down. Now, this is always something that puzzled me for a long time. I think I figured it out. What's an index refraction? Everybody thinks that they know what it is, right? You're in water, the pencil looks like it bends because the refractive index is there and all this. Well, it's not that easy. So it's not a particle of a property. Refractive index is a property of a substance. If I have something like this, it's the weird composition. It doesn't make any sense to talk about refractive index of a particle. Okay? And I hear people talking in the field about refractive index of particles, refractive index of an aerosol, which is a collection of particles. I don't think they know what they mean either, but I certainly don't. Okay, in general, what do we have? We have our polarization. It's the opposite side of the electric field, opposite direction. So I get a negative, and it's this I have a vector and a vector. What connects two vectors if I have one by another? A tensor. That's just the way it is, two-dimensional, because I can have a force in one direction, electric field in one direction, and a polarization at some odd angle. So this is the identity tensor, and this is the polarizability tensor. That gets a little awkward. We're trying to make things simple. So I'm going to have a uniform particle where everything's nice. And now these are scalars. If the polarization goes in the same direction as the electric field, or opposite direction, but the same line. It's epsilon -1, and my index refraction is the square root of my polarizability. So I can define an index refraction for a nice simple quantity, a substance, but I can say this particle now has this index refraction. But he's with me so far. A little tutorial on me scatter. Okay, so the index refraction is the measure of how strong this substance interacts with the electric field, like my dogs, how strong my leash is. Does the dog really pull? Does it just go a little bit? That's my polarizability, which I quantified by my index refraction. Now we're ready for me scattering. This is just to show you how the sausage is made. I don't expect anybody to follow this, but I'm going to go through it just so you can see what goes on. This is several weeks of class right there. So what am I going to do? I'm going to start with Maxwell's equations. Okay. We all know Maxwell. We'll put those up. You don't remember. We're going to solve the wave equation. I have a wave equation outside the field. I have a wave equation inside the field. I'm going to match my boundary conditions. Then I got to expand my incoming plane wave into a mathematical form that's going to be useful for me. I solve for these quantities A in and B in, and I use those to find my Q scattering. Okay. So this is what we're going to do. I'll slowly walk through this. Maxwell's equations. One of the most brilliant constructs of human existence. Relates an electric field E and a magnetic field B. We know our epsilon. This is our charge density. This is our current over here. This is we can call this 1. Sometimes it has units depending on it, but we don't worry about magnetic stuff. We're just worried about epsilon. So this says I don't have any magnetic monopoles. Okay, there's no divergence of my magnetic field. This says that if I don't have any charge there, I don't have any electric field generated. This says, oh, these get nasty. Remember curls where things go sideways and oh, okay. This is a little messy. So this says if I have a changing magnetic field, my magnetic field changes with time, I'm going to generate an electric field. And this says, well, if I have an electric field that changes with time, it's going to generate a magnetic field. So what's a plane wave? I have an electric field that's going. That generates a magnetic field. That generates an electric field. Okay? So this is how we propagate light. Everybody's with me so far? Not? Speak up, ask questions. Okay. This is our boundary conditions. I've got inside this is the whole sphere now. So inside the sphere is 1 and outside is 2. And I take my four Maxwell's equations. Anybody remembers this? You make a little control volume and you match fluxes in and out, and the dot product of your normal vector on the outside has to be the same as on the inside. And oh, we got these nasty cross products now, which things go this way, get coupled to things going this way and this way. Messy math, okay? But math is important. That's the essential part, okay? How do we get to 3 dimensions? Okay, we have a wave, which is a vibrating system. We're going to build it up. Start with 1 dimensions and 2 dimensions, and now I've got this wave and a sphere, so I've got 3 dimensions. So 1 dimension we know, right? We have a lot of things that are one-dimensional. Whether the wave is transverse, like a pressure wave, or longitudinal, like a pressure wave, or transverse, like a guitar string. So take a wave on a guitar or a string on a guitar, pluck it. We fix boundary conditions so we can get several different modes here. Everybody's had this in some physics, right? We know so far. If I have a wind chime, not the collection of them like a guitar, but just one, I thump one and I have a pressure wave going in and out. So they all kind of look like this. Okay, and this one, number 2, for instance, had the node right in the center. So when it vibrates, it's going to vibrate like this. I was trying to find a little stringed instrument and stuff to bring, and I just never found one. We can build up any shape here in terms of sines and cosines. And you know this is basic Fourier series, right? For my string with fixed boundary conditions, I only have my sines, I don't have an A naught, but in general, I have a cosine and a sine. We have fixed boundary conditions, and I can build up anything. Basic Fourier analysis. Everybody said Fourier analysis, right? Yeah, good, okay. Everybody's with me so far. Okay. Well, my fundamental frequency is the frequency at which number 1 vibrates. The second mode, number 2, vibrates at twice that frequency. The third vibrates at 3 times that frequency, and so forth. So if I take a single string and pluck it, no matter what it's vibrating, there's this reinforcement. It kind of has a nice tone, right? A single string, and we can tune them together, but just any one string here is going to have a nice tone. Same thing here on the flute. Same thing on a wind chime. It's going to have a nice, kind of a pure tone. Okay, we'll get to that in a minute. Remember that thought. Now we go to 2 dimensions. A drum, right? We have a drum head. And these are the modes of vibration on a drum. I can have the whole thing going up and down. I can have the whole thing going where the middle's going down and the sides are coming up. This vibrates. Or I'll have a circular node. I can have a third one where it's a ripple thing, but going back and forth. No, drum's a vibrating system. Why does a drum not sound musical like a string does? Right? But that strings sound kind of good and drums don't. Why is that? Okay, that puzzled me for a long time. Somebody explained it once. I thought that's clever. Okay. I forgot. 2 dimensions, what do we think of? Bessel functions, of course. You knew that right away, right? Yeah. Everybody thinks Bessel functions. As soon as we have a circular thing. Okay. So these are our Bessel functions. They're not sines and cosines, but they're J's. And J's aren't too bad. So they kind of look like a sine and cosine, but they're decreasing. So this is like your first sine, and this is like your second sine wave. So in 2 dimensions, our radial coordinate is a Bessel function, or a radial function. And then going around the circle, we have sines and cosines. So this is like a 2-dimensional circular expansion of a Fourier series. It's a Bessel series. It's just like a Fourier analysis, but we're doing it in these terms. Right, we can do that. We know what Bessel functions look like. They're not too bad. But what are ratio of frequencies? Well, the second frequency divided by the first is a ratio of 1.59. And the third frequency is 2.14, and then 2.3 and 2.65. So if I pound on a drum, all the higher frequencies don't really match up well. It's got a fundamental tone. I mean, I can tell you that this is going to be a deeper tone or a lower frequency than maybe this one or this one. But other than that, it doesn't sound nice like a guitar string because my frequencies don't line up. Okay, little physics, so I thought it was pretty fun. 3 dimensions, okay. 1 dimension, you think of sines and cosines. 2 dimensions, you think of Bessel functions. Come on. What do you think of in 3 dimensions? You won't. Oh, you're shy. Okay. 3 dimensions, the first thing that pops into your mind is, of course, spherical Bessel functions. You knew this, right? Okay, well, they're kind of like Bessel functions, or a little j instead of a big G. And they look like a sine wave and a cosine wave. They're oscillating, but they decay. And in fact, they are pretty closely related to your sines and cosines. Okay, so your zero spherical Bessel function is a sine x over x. So it's just a sine wave that decays as I go further out. You should have made this r for radius. My first Bessel function is a sine and a cosine, and it does this. So they're oscillating and they're decaying as I go out. We can look these up in tables. These are going to be important. Okay. I expand my scattering wave. I kind of cheated. I didn't tell you what U and V are, but now I've got my wave. I'm expanding it in 3 dimensions. I've got cosine and sine, which is this part of it. I've got the p's, which are associated Legendre polynomials, so the first type. I've got my h's. Well, h is a combination of a spherical Bessel function, j, and the n kind of spherical Bessel function, which are the nasty kind, okay? So there's bad kinds. There's good kinds and bad kinds. So I make it a complex thing. This one minus I times that one, where I is a square root of -1. I get my Hankel function. So these are my Hankel functions. So I do this expansion. Not trivial, but this is just a glorified Fourier series in 3 dimensions. Okay, this is from Mie's paper in 1908. Remember how on a guitar string, your note is in the middle, it stays there? On 2 dimensions on a drum, you might have a node here that one side goes up and the other goes down. Mie drew these in 1908 as do the electric and magnetic fields of the first modes in a sphere, which I thought was pretty clever to do pre-computer 100 and whatever. Okay, now we go back. Remember our A's and B's in our expansion here. We have an A as a coefficient here, and a B is a coefficient here. And we match our boundary conditions and we spend 3 or 4 pages of doing math. And now we solve for A's and B's. Bear with me, almost done here. Okay, A is this mess divided by this mess, where my psi is a spherical Bessel function, or a big Bessel function of a half order, times the square root of x, and this one is a Hankel function, which is the good Bessel function with the nasty Bessel function. And I calculate my A's and B's. Okay, we're almost there. And then after the A and B, I make my S1 and S2, which are my 2 polarizations. And oh, I forgot to tell you, your pi is related to derivatives of the associated Legendre polynomial, and your tau is also. And I get my phase function. And then I do this, where this is a complex value squared, and add them all up. And I get my scattering. Easy as pie, right? Okay, that's what it takes to make it. Now, we'll see, Daniel. Can you help me out? We got a video clip I thought would typify what was going on at this point. Let's see if we can do this. Right. And then volume, you have to hit volume up as it starts. There we go, yeah. Okay. Oh. Turn up on the computer.
Yeah, it's full on. Where is it here?
Off the speaker.
Speaker.
$37 billion loss.
You back to the first thing, yeah.
Taxation on GFP of 39%, doesn't it?
Stop that. Yeah. Can we recycle?
Same.
Okay, this is from Saturday Night Live about 45 years ago, a presidential debate, and I thought it summed up probably what's going on.
I don't have a.
It was my understanding that there would be no math.
Okay. Thank you. That's good. We go back. Okay. They bore him with facts and figures, and he goes, "Yeah, my understanding there'd be no math in this debate."
We go back here to. We were here.
Okay. There we go. So I've shown you the math, some of the math. I skipped some steps that goes into calculating the scattering. It's very mathematical. I've got an electromagnetic wave that's got perpendicular dimensions that have cross products and nasties in it. And I've got a sphere, which is not the geometry of a plane wave, right? So we do all this and we get our answer, but there's not a lot of physical insight. And I don't like physical insight. So we can think of Mie theory as a black box. I put in my diameter of my particle, my wavelength, and my index refraction. This black box churns away and spits out tau's and pi's and a's and b's and comes out with my phase function and scattering. But I don't like black boxes. I never did. I want to understand what's going on because otherwise you got to trust somebody else. And I guess I'm not a trusting soul. So we're going to try to see how the black box works. So after the talk, I'll show you what's in the black box. Okay. Remember what we want is Q, which is the ratio of energy scattered to the geometric cross section. So we go through our Mie calculation. We want to see how it depends on the variables that put in. So first, the dependence on diameter. We put that in and we get this. Wow, this is very rich. I picked an index refraction typical for atmospheric aerosol particles. I picked a wavelength. I could have picked anything that's going to look the same. This is my diameter up to 10 micrometers for a 550, which is green light, like the laser pointer. And what does my Q do? It starts at 0, it goes way up to almost 4.5, it goes down, it goes back and forth. Extremely rich, complex pattern here. And it's decaying, so we can see it kind of levels off. This is 2, just to draw a reference line. Okay, so this makes our life harder. If this was nice and easy, then I can find my scattering cross section, I'd have it. But there's a lot of richness here, a lot going on. So we're going to have to delve into this a little more. So this is the curve again up here. And I say, if I just take this part here and blow it up and expand it, well, we got these little spikes, these resonances, right? Imagine doing a frequency sweep. I fixed frequency and sweeping diameter, but I could equally well do the other way. Every time there's a spike, that means I've got a resonance going on, right? So I'm sweeping this and I hit resonance at all these odd places. I get an overall wavy structure. And then on top of that wavy structure, I have other wavy structure. And then I'll take just this little part here. I could have picked any. Just this little part here and blow that up. And I get these spikes here that are real. This is not just a calculation bit. This is real. So I've got this resonance right here in the middle of nowhere with nothing on either side. Very precise. Very useful if I have a single particle in a, let's say, electrodynamic balance. I get an aerosol particle, electric field, quadrupole. Everybody's done this for a long time. And sit it there, shine it with the laser, and change the relative humidity, which changes how much water it takes up, which changes the index refraction. For specific combinations, oh, I'll get this big spike. So I can lock onto one of these and trace it now and get, they're doing like 4-digit precision and accuracy on index refraction of particles. Using Mie scattering on this for a single particle. I'm interested in it for aerosols, meaning a collection of particles made. So we have an extremely rich pattern of Qs going on. Okay, let's look at this. So for small particles, but smaller than the wavelength, my wavelength's 550. So I'm looking over here at very small ones. It goes like d to the 4th. It goes like a 4th power. You might recognize this from your classes. And this, my range of interest doesn't show up. Okay, I put a gray box up to about a micrometer is my range of interest, right? Most aerosol particles I care about, a lot of them are between 0 and a micrometer, or 1,000 nanometers. So they come to about here. So over that range, I go way up and I come back down. A lot going on. Okay, this is an interesting one where the whole lecture of itself, the very big particles, this kind of approaches 2, which means if I have a basketball here and I have a plane wave, this big particle scatters twice as much energy as the surface area. So if you really want to make me popular, go ask your professor to explain that in a simple way, why it's 2 and not 1. Called the extinction paradox. Okay, I'm going to leave it at that. Okay, this explains why we have white clouds. This explains over here at d to the 4th why we have blue sky and red sunset, right? You've had this in class. Why is the sky blue? Because we have Rayleigh scattering. Particles much smaller than a wave. Okay, we're back to our, not dogs, we're electric field. This is my electric wave, right? It's the electric field. It's pointing down and 0. It's pointing up and up and up and down and down. And it's moving this way at the speed of light. So here's a particle here that's much smaller than the wavelength in diameter, okay? So what happens? What does that particle see? Well, over this range of the diameter, all my electric fields are pointing up. So the particle polarizations are all going to be pointing down. They're going to be pretty much in phase with each other, right? So this wave goes through, and once this gets here, over this diameter with here d, my electric field is all going to be pointing down. My polarization is all pointing up. Everything on that particle is feeling the same electric field. So we get a dipole, right? I can treat this as just a single vector going up and down. And this is our Rayleigh scattering. The scattering efficiency is given by this. It's like d over lambda to the fourth. Everybody's seen this. So good. Mie scattering tells us something that we already knew, but in a very mathematical way. Let's go to the other extreme. Now I have an electric field that's rapidly in short distance oscillating up and down and up and down, and I have a bigger particle. Well, this part of the particle is seeing an electric field go down, so its polarization is going up, and right next to it's going down, and right next to it's going up. So what happens is my electric field goes by. Well, this part of the particle has electrons moving down and then up and then down. This one has electrons moving down and then up and then down. The next one goes the other way. So I have a very confused particle here, right? It doesn't know what's going on. Remember from Maxwell, if I have a moving charge, my electron, that's a current, that creates a magnetic field, and I have a moving magnetic field that creates an electric field, and what happens? This particle is radiating. Every part of it's radiating, but out of phase with each other. So I have all these weird interference patterns. And that's what gives us the little wiggles and the spikes on the little wiggles and all that. Again, I wish I had better intuition where I could explain it. I don't see how to get that out of here. But we can do the math. Okay. Now, how does it depend on wavelength? We've seen how our Q depends on diameter. It goes up, oscillates, and it levels off to 2. How does it depend on wavelength? So I'm going to pick a fixed index refraction, 1.5, and now as a function of diameter, I've graphed my scattering efficiency for 3 different wavelengths, red, green, and blue. And these are our typical ones. We have aerosol measurements in the laboratory. We look at what's the red, green, and blue. So for smaller particles here, my blue scatters a lot more than the green, which scatters a lot more than the red. We kind of know this. This makes sense. And in fact, if I were to take an instrument from our laboratory, we have one of these down the hall, a nephelometer. What's a nephelometer? I blow air through it. I have 3 different color light bulbs, red, green, and blue, and I calculate the amount of scattering from each. And I run air through it first with a filter. I subtract that out. So what I'm getting is the scattering from the particles. Well, my blue is bigger than the green, bigger than the red. This is kind of what we expect, okay? Makes sense. That's why the sky is blue, not red. That's why sunsets are red. This is all perfectly making sense. And if I get bigger here, they all kind of get bigger because I have a lot more of the stuff in the air. And if they get smaller, they all get smaller, have less of the stuff. We can use the distance between these or the relative magnitudes to tell us something about the size of the particle. Okay, let's go back to our original graph. Red, green, and blue. What happens if I go over here to a micrometer though? Ooh, things turn around. My red scatters twice as much as my blue. Okay, and my green somewhere in between, but up here my green scatters more than the red and the blue. And this happens actually. He's not here anymore, but he used to have the office next to me and he was doing some measurements in the Azores, right by the coast. And he goes, Ernie, look at this. I have more red scattering than blue scattering. So we figured there was breaking waves and it was just the right conditions to get a lot of sea spray particles that were mostly right in this range where they're going to be dominated by red scattering. There's a few very famous papers in the literature that there was a forest fire in Canada. By the time it got over to Britain, you know, the particles had processed and coagulated, but they were right in this size range. So they get the blue moon effect is what it's called. You get these weird effects where the red is scattered out and what's left is the blue. So that this weird stuff. So you get all sorts of interesting phenomena here. But for lower diameter particles, most of the size range we're interested in, the blue is going to scatter more than the green, more than the red. Now, had we've been clever, we could have done this initially. I'm going to take the red, green, and blue, and I'm going to plot them now on a different axis, which is just the diameter over the wavelength. Let me go back. Notice how all these look like the same shape. If I just take the red and scatter it over, stretch it, move it over to the blue, and the green, they all fall on one axis. That makes sense, okay? I've got index refraction, which has no dimensions. I've got my Q scat, which I've dimensioned a lot, made non-dimensional. I've divided by an area, so that's dimensionless. I've got 2 quantities that have dimensions, diameter and wavelength. The only way that works is it depends on the ratio of those. Okay, so that helps us some. That reduces the problem. I've gone, instead of being a function of d and lambda and m, it's a function of d over lambda and m. I've gone from 3 quantities, 3 dimensions to 2 dimensions. That always helps, right? Now let's see how our scattering depends on the index refraction. So now the colors are just to designate different indices of refraction. I pick 550. This is my diameter, and I pick different indices of refraction, 1.4, 1.45. There's about 1.33. Dry ammonium sulfate, dry sodium chloride is about 1.6, 1.63, somewhere in there. My polystyrene latex that I use in my aerosol laboratory, which is a polymer, the calibrate instruments is like 1.59. So this is your ambient range in the atmosphere. This is what I care about. Kind of like this, you know, red is 1.4. If I pick a 500 nanometer particle, 1.4 index refraction scatters less than 1.45, scatters less than 1.5. This makes sense. Remember, index refraction is a measure of how strongly the substance interacts with light. So a bigger index refraction means it's going to interact more. I'm going to get more scattering. Well, what happens over here? Again, we get these weird reversals where over here, the lower index refraction scatters more than the higher one. And this is my case of my confused particle, right? Well, part of the particle's going up, part's going down. And I get these weird interferences. Again, I wish I had a more intuitive feel that I could, for this, I could explain, but I don't. Now we're going to do something that I thought was clever. I make another dimension coordinate, which is 2 pi d over lambda times the index -1 and plot it versus that way. And again, it's like with the different colors, they all pretty much lie on the same line. Okay, people have known this forever, but I didn't think anybody had really exploited this much before. This to me is like, wow, anytime you can reduce the dimension by 1, you're doing great. Okay, so we've gone from 2 dimensions, d over lambda and m, basically 1 dimension. I have 1 parameter that's going to explain most of my light scatter. 2 to 1, this is a big deal, okay? So that's my first accomplishment. Not mine, but the first accomplishment of this, okay? So a good approximation, the light scattering from a sphere only depends on this one quantity, C. And it depends on the scattering of scattering on the wavelength, independence of scattering on the diameter, independence of scattering on index refraction are all kind of combined into one. They're all related. Okay, let's go back to this. That's all been known so far. This is new. Whether it's a big deal or not is up to you, but I kind of think it is. There's some stuff, mileage I can get on. I can fit this pretty well to a single function. Nice analytic result. Well, an analytic result in my mind is much better than our Mie coefficients, which is an infinite series of the nasty Bessel functions and all this stuff, right? So I can fit this and go, this is going to cover most of what I want to cover as far as mathematically explaining my Q scatter. Okay. It goes as z to the 4th here, which is good. That's my Rayleigh. Up here, I generally don't have many particles above 100 nanometers, or if I do, I'll put an impactor on. And typically they do impactors to get rid of it. So I don't worry about this. It covers me up to here, which is where most of my scattering generally takes place. And if I'm really worried about this, I could fit another one that would pick up the next hump on there. So this is good for here. The wiggles don't really matter. I'm within about 10% here. One, you can't measure particle diameter or concentration within 10%. Second, if I've got an aerosol, I've got a spread of a range of particles so that, yeah, this diameter I underestimate by 10%, this I overestimate by 10%. That's going to average out unless I have a very, very narrow particle. If I'm doing a single particle electrodynamic balance, I'm going to do my full Mie equations. But if I'm doing an aerosol, I can do this. And this covers exactly what I want. So I call that accomplishment 2. Okay. So good approximation, this is my scattering efficiency. I call it Q gamma because it's a gamma function. Gamma functions are nice. We like those. The aerosol world tends to live in the log normal world. The gammas are just as good. NASA fits their radiation retrievals of atmospheric aerosols to gamma functions. Okay, I have a graph at the end. If we have time, I can show you where I'll challenge you to tell me which one's a gamma function, which one's a log normal, right? It's just conventional we pick log normal. So gamma function's convenient and easy. That's nice. Okay. One thing this does, if I want to calculate my total scattering cross section, I can do it in one line of code. I was talking to a friend from NASA last week. They've got lookup tables. You're running your global climate model, and you've got to go, oh, with this diameter and this index, I got to pull from a table and do that. That's incredibly expensive from a computational point of view. So what's my total scattering for my aerosol? Well, I break my aerosol into little size bins, right? We always do this from 100 nanometers to 110 and 110 to 120. And for each size bin, I take the number of particles in there. I take the cross-sectional area here, and I multiply by my Q, which I can calculate right here, just in one line, and I add them all up. My computer code's gonna go a lot faster now, right? I have a one-line calculation of my total scattering cross-section. Okay, that's pretty good. If I have, okay, talk about that next. If I have a gamma function as my size distribution, I make my sum an integral, and a product of two gamma functions is also a gamma function. I can get an analytic result out of this. Right? So you fit your size distribution to a gamma function in one line, I've got the analytic result for the scattering cross-section. To me, that's a big deal. Okay, what's the angstrom exponent? Angstrom exponent explains the wavelength dependence of scattering. So it's the negative logarithmic derivative of the scattering cross-section of the derivative of the logarithm of the wavelength. Okay, well, remember, I'm doing a logarithm. The logarithm of z, in my z, my lambda is in the denominator. So all that does is get rid of the negative sign. So all that angstrom exponent means is what power law does the scattering go by? So it goes like d over wavelength to the lambda, or alpha power. Alpha is my angstrom exponent. Well, we know for small particles, it goes to the fourth power. That's our Rayleigh scatter, right? For big particles, there's much less of a wavelength dependence. So my alpha depends on the diameter. Right, I said that, okay. My Q gamma, if I plug it in, it's this nice little result. It's pretty amazing. Then my angstrom exponent is 4 minus z. So I can calculate z from my diameter, index refraction, my wavelength, and I can tell you what the angstrom exponent. This whole thing came about for me ages ago when I'm like, you know, everybody remember the red, green, and blue nephelometer. People like do all the calculations, go, well, your angstrom exponent's about 2, you know, and above 2 is really small particles, and between 2 and 1 is medium particles, and less than 1 is really big particles. What's small? What's big? I needed an analytic result, you know. What does it mean to have an angstrom exponent of 2? And this pretty much tells me. I can calculate it 2. I can tell you what the diameter is that's going to give that. So I consider that accomplishment 3. I've got an analytic result for my angstrom exponent. Now, if I have a distribution of sizes, it's slightly modified, but this is a basic term. It gets weakened a little because I have a spread of particles, meaning there's some bigger ones and some little ones, and the bigger ones weigh more. But I get a simple result like this. Okay. Aerosol index. Don't worry about the math. I'm just going to blow through that. What's the aerosol index? Well, NASA derives this thing, or somebody proposed this, called the aerosol index, which is a product of your aerosol optical depth times an angstrom exponent. Aerosol optical depth is just how much light scattering do I have in a column above me. Okay, we're talking about light scattering cross-section of a particle. And then if I have a bunch of particles, I get the scattering coefficient of an aerosol. The optical depth is just how much of that there is looking toward the sun or looking down from my satellite. So it's the same thing. But I go, well, this is where this is a quantity here that I talked about, like my Q, and this is an exponent, which why would you multiply these? But we can go through for my Q gamma approximation. I can get a nice analytic result of this. I think that's something because I read all the literature I could find about it. Somebody proposed it. Sometimes it works, and somebody goes, yeah, but it doesn't work here. And I can go, oh, I get an analytic result, and I can tell you if it works, why it works, and if it doesn't work, there's a physical explanation. So I'm big on physical explanations. So I thought that was kind of cool. And finally, winding down, thank you for your patience, the light scattering dependence. This is a biggie, right? I have fog, I have things going on, I have a humidified, you know, HTDMA or something, or a humidified and dry nephelometer. I want to see how in the atmosphere, the light scattering of an aerosol depends on how it uptakes water. That's an important thing that people want to measure. And I know for diameters, my diameter ratio of 2 wavelengths for a given particle is independent of the size of the diameter, for the most part, unless I get to form clouds and have to worry about surface tension. RH is dimensionless, so D, a ratio of 2Ds has to be dimensionless, so it can't depend on diameter. There's no other physical quantity that's linked. So this means if I have a particle that's 100 nanometers and one that's 200 nanometers, and I put it at a different relative humidity where this one goes to 150, this one's going to go to 300. They all scale the same. And everybody kind of assumed that worked for light scattering also. What does it do for my scattering cross-section? Complicated math, don't worry about that, but it doesn't. If I do my ratio of scattering cross sections at two wavelengths. This term is only a function of my relative humidity. This is only a function of my relative humidity. This is only a function of my relative humidity. This has a diameter in there and a wavelength. So this means no, my light scattering is going to depend on the particle size. If we have two aerosols, you have aerosol in a box here, aerosol in a box here, and these are smaller particles and these are bigger particles. And I increase the relative humidity and they both swell up the same amount. One of them is going to scatter more proportionally than the other. Okay, and that's big. The literature hasn't quite determined that yet. Okay, so that would be something, if I'm going to write up, would be the first one to do. They're trying to fit it exactly like they did for the diameters, but functionally you can show that doesn't work. Not physical. Okay. Okay. With that, let me sum up. It's all about me. You hear statements that go, well, here's the Rayleigh range, and here's the geometrical optics range, and in the middle I have to do Mie scattering. No, it's all Mie scattering. There are limits at the lowest particle diameter compared to wavelength and high particle diameter that have other approximations that might be easier, but Mie scattering explains the whole range. It's kind of like a black box, though, as you saw. You were very patient to follow through the math. Doesn't really give a lot of insight. So it's useful, it's a necessary tool, but it's not quite there. Reducing dimensions is always good. I would rather have one variable to work with than three. So we go from here to here, which is obvious. And I thought what was new is going from here to here. So we're going from 3 dimensions to 1 dimension. So the diameter, the wavelength, the index refraction are all coupled in the scattering. That's kind of good. And then what's new? Approximation can be quite useful. I make an approximation, which is, it's going to give me 90% of what I need. It avoids the use of lookup tables. It gives me a one-line result for the total scattering cross-section. It gives me an analytic result for the total scattering cross-section and angstrom expert. It gives insight into the aerosol index, and it relates to wavelength dependence of scattering and the relative humidity of scattering. That, think outside the box. This is my message to students, right? We talked about me being a black box. Don't go through it. Go outside the box. We come up with Q gamma of one variable. So think outside the box. That's my clever little. With that, I thank you. I'm ready for questions.
Oh, wonderful, great. I brought up memories for me. Your Maxwell derivations reminded of my oral exam as a bachelor, and I'm not sure if I did very well in that one.
Trauma for many of us.
Yeah,
right?
drama. I couldn't do this integral over 3 dimensions. It was just, well, anyway, I still enjoyed. Now I understand better. So we are open for questions.
Who's got the first question? Come on, somebody. I can't have explained it better.
My first comment, you're hired, Ernie.
Yeah,
Thank you. I might be looking for a job. Yes.
there was someone's like, okay.
Any-
As an experimentalist, is there anything we could do in the lab to kind of validate what you've been seeing, and what would your idea be? Because like, don't we have to use those calculations for like an nephelometer?
So with the nephelometer, the little relation for the angstrom exponent to the size, you go, well, here's my nephelometer, here's my angstrom exponent. I can get, instead of going, well, those are big particles or small, I can go, most of the scattering comes in the range 200 to 250 nanometers instead of 100 to 125. That's insight, which I think is valuable. I could certainly foresee doing experiments on the light scattering cross section. The light scattering, relative humidity depends on light scattering,
Yeah.
right? You take an aerosol, you're flowing it through, you humidify it, look at the light scattering, and then show how it follows this. Because the literature's noticed that. They go, well, we do this approximation, but when particle sizes get bigger, it doesn't quite follow it as well, so they're smaller. We know that. When they're small, they go like d to the 4th. My d swells up by a lot. When they're big, they go like d squared. D to the 1st, it's not going to swell up as much. So we know it depends on diameter, but we can do those experiments to do them.
Yeah,
That's a very, very good question, though, as to what new experimental Well, do experiments with this in general. Yeah, very good question.
So I want to follow on to that,
Yes.
is we saw this in the field. So the first 2 years we flew during the dry season in our AOD, the aerosol optical depth was about 0.4, which is decent.
Yeah.
But we then, the third year we flew in the wet season and the AOD was, I don't know, 0.7, 0.8, and as a aerosol person, I was like, oh my God, we're gonna see so many particles, the concentrations are gonna be so high, and we saw almost nothing, and all of our stuff is dried when it comes through the plane, but all of the remote sensing stuff was getting all these crazy high AODs, and we think because the particles were swelling, yeah.
It's something I've always been interested in. Almost all the aerosol measurements, they dry the particles to measure.
Yeah,
Well, we do that because there's such a strong relative humidity dependence, and relative humidity dependence has such a strong, relative humidity has a strong dependence of temperature if I have an absolute humidity. So if I bring it into my instrument, which has lights and motors, and I heat it by 2 degrees C, I've changed the relative humidity by 10%, which is huge. So we dry them all, so we don't have to worry about that. Well, that's great, but in the real world, they're not dry. They're at 80% relative humidity or something. And how do we go from a dry to a hydrated? And that's another talk, but that's something that has been a focus of interest for me for a long time. Now, very good question on what experiments could we do for this. Thank you.
There another question? I have one online question here by Ogo. And Minghua Sang posted another one. So let's go with Ogo's question first. I love the talk and the dog walking squirrel analogy. Does the approximation apply to particles that also absorb light, or is it just for pure scatterers? And you didn't talk about absorption and absorption will affect.
Absorption is a very big topic. I just touched a little bit of the, right? I did purely scattering aerosols. If I have an absorbing aerosol, we model that by an index refraction. It's a complex number. All scattering particles or all absorbing particles still scatter light. So it's not that I have some that absorb and some that scatter. They all scatter, some also absorb. And I've been working on that. I haven't come up with something as simple as this. It gets, as you can imagine, a higher level of complication. But no, I would like to extend it and go, okay, I can certainly do if I have slightly absorbing, right? I can still, find what my scattering is and my absorption is and all that. But no, in general, yeah, there should be something simple and simpler instead of doing the whole Mie calculations on that, I would think.
All right, and then maybe we give the last question to Minghua Sang, which goes in a similar direction. For radiative transfer in the atmosphere, do you have a simple formula for the absorption efficiency and the asymmetry factor?
I do for the asymmetry parameter. I didn't show it here. I don't know if, to be honest, I don't know if I do for the absorption. I've been playing with it, and Daniel twisted my arm and said, you got to give this talk. And most of this stuff I did years ago. So I'm pulling it up, relearning it. I thought I had played with that once. I don't have anything publishable that I could do, but I'd be glad to talk about it.
All right, wonderful.
Is this Minghua?
Yeah, that was Minghua.
Oh, I have. Okay, let me show 1 or 2 slides here for
Okay.
Minghua. So I promised you at the end, if you're nice, I'd show you what's in the box. Minghua will appreciate this. Okay. Minghua knows this person. Probably most of you others don't. This is Warren Wiscombe. Warren was a buddy. He was at NASA for a long time. He's worked with Brookhaven for a while. And in 1980, Warren had done a pretty seminal paper on calculations of light scatter. I'll let you guys read this, and the younger people are going to go, understand. Okay. Read it? So,
Thank you, Ernie.
calculations.
He says thank you, Minghua.
Minghua, I knew Minghua would appreciate it. He knew Warren too. Computers aren't like you pull it out now and you can do whatever. I mean, they didn't have tables of Mie scattering. Basically had no citations for like 40 years because there were no computers that could do this. So I got this infinite series of these nasty spherical Bessel functions. I got a calculator, you do it by hand, and somebody published a table of 1 index refraction, 10 diameters or something, and that was a year's worth of work. And now computers do all this. But back when Warren was doing this, things cost money. I mean, computationally expensive. A multiplication was much worse than an addition. So Warren came up and goes, I got this new way to do it. So if I do recurrences this way, Dave did it. Dave needed 6 multiplications and 4 additions. You do 3 multiplications and 3 additions. And that was worth implementing because it saved And here, he went from, remember I showed you, I don't remember, I had an S1 and an S2. Well, if you took the sum and then the difference, he gets one multiplication and one addition instead of two multiplications and one addition. So he saved a multiplication. It's like, you know, your grandparents going through the Depression saving pennies and bread wrappers, where now you're like, we're rich. I mean, we're basically rich. Your computer, I can do Mie calculations instantly on my computer. It does all the Bessel functions and everything's just, wow. But back in 1980, it was still a labor to do this, and you want to make it as efficient as possible. So I thought about this years ago. I always wanted to do this. Warren's in the black box. I thought he would appreciate it.
So we are in principle over time, but there is a question from one grad student.
Okay.
Therefore, I want to pose this question on like by Jiaojuan Miao. Great talk. My question, bravo. My question, when we apply the simplified parameter Zi, or does it mean that we kind of ignore the characterization of the particles themselves? Because for LiDAR retrieval, we really need the particle information and we still need lookup tables. So,
Well, when you say you need particle information, okay, LiDAR, you do a lot of things. They're not all spherical. So if I have a dust particle or a sea salt that's dried out, it's not a sphere, so I get a depolarization ratio, right? It's not simple anymore. I've got my perpendicular polarization and my parallel. And remember, our electric field goes one way, the magnetic goes the other. Well, what if I rotate it? My electric's going this way, my magnetic's going the other. So if I send an electric field pulse that goes in this way, and the particle sends back, reflects an electric field that's going that way, I've depolarized it. That's a very important thing for LiDARs. They tend, oh, I was probably off the camera. They tend to do that. If you're in a range in the atmospheric boundary layer where you're high humidity and everything's spherical, then you don't need polarization. And you're coupling, the Z parameter couples the particle information. It couples the diameter with the index of refraction. It's not going to work for everything, right? It's not going to work for dust if I'm aspherical, if I have other types of particles. But in some regions, it could be where you don't need lookup tables. And I would say if you're not spherical, what's your lookup table going to be? You don't know what shape this dusting is. So I would say this could be applied probably to most LiDAR problems and avoid the need for lookup tables. So that's a challenge. We can be glad to talk about this.
Okay. All right.
Okay.
With
Thank
that,
you for your attention.
yeah, we thank Ernie for this great seminar, and as usual, lunch is served.
Thank you very much. I'm done with it now.
Yes.